You're given region R and you're trying to integrate this function over region R. So the question, I didn't fully write the question. The question is integrate this function over this region R. And dA means it could be dy dx or dx dy. And our goal is to actually be able to represent this integral as dy dx and dx dy. Now, as you know, hopefully you know that if you have, say, dy inside, then the things that you write here are y equals to something. Even if you don't see a y, it really means y equals to something. And because for double integrals, the inner one can have, it can be a function of x in here. The outer one has to be a number to number. You can never have an x or y at the outside. But inside, if you have a function of x, then y equals to a function of x gives you two graphs, right? In other words, you get curves on the two-dimensional coordinate plane. So when you see dy dx and you see a double integral like this, you should always think of it like going from curve to curve, and then once you integrate, it's going from point to point. Okay, so let's look at region R. Region R is, if I say this is 5, and if I solve this for y equals to 3x, so multiplying by 3 both sides, I get y equals to 3x, so that's a very steep line, whereas y equals to x is this line. So it's something like this. It's the domain that's bounded by these curves. So that's what we have. And then you're supposed to be able to paint this region R either horizontally or vertically. Now if you try to do this horizontally, you realize that there's something that happens at this point. I don't know what, oh, that should be like 5. Okay, so this would be 5 comma 5, because this is y equals to x. Y equals to x. If x coordinate is 5, the y coordinate should be 5, right? So above 5, you start from this line and ends up at 5, whereas below 5, you start from this line and you end up at this line. So the beginning and end is not uniform. Sometimes you use this, sometimes the ending part is sometimes this or sometimes that if you paint horizontally. That will make the integral only to be expressed as two integrals. You can't express it in a single integral, you have to use two integrals. On the other hand, if you were to paint the same region vertically, say going up like this, then you always start from here and you end there, right? So for this case, painting upwards gives you an easier access to the integral. So painting upward means you do dy first, you go up. Dx dy means you go right. So I'm saying that dy dx is easier, so let's try this one. Where do you begin? You begin here and you end here, something that's more steep, and then you go from 0 to 5, right? 0 to 5. And then you're trying to integrate f. Okay, let's continue. Let's write down exactly what I mean by that. So this curve, this one has the equation y equals to x, right? And this one has the equation y equals to 3x. And really you don't have to write y equals because this is not necessary. You can just write x and 3x, because if you put dy here, that means anything you write is really y equals and y equals. So you have to keep in mind that even if you see just x and 3x, you should always think of it as y equals to x and y equals to 3x, okay? Then so you also have dx, so you have dy dx, and then the function that you're integrating is x squared e to the x squared. So that's how you represent this using dy dx. Now on the other hand, what would happen if you try to do dx dy? If you paint the region sideways from left to right, as I commented, it should be two integrals. for two different cases. When y value is from 0 to 5, you get one integral, and then what is this point? Well, this equation is y equals to 3x, so if this is y equals to 3x, when x is 5, y would be 3 times 5, so this point would be 15, right? So from 5 to 15, you would have another expression. Okay? Now let's continue. So what is this and this? Well, below 5, you start from here and you end there, right? Now, although this one I said it's y equals to 3x, this time I would like to use x equals to y over 3. Why? Because I have dx. So you should write down the equation as x equals to something. X equals to y over 3, and we don't write x and just write y over 3. And then it ends here, which is x equals to y, so y goes in here. Okay, so it's very important that although I'm writing y and y over 3, you should really interpret this y as x equals to y, which is this curve. Okay, I'm calling it a curve because in general, if you have y equals the function, it's a curve in two-dimensional plane, right? Although this is a line. So we go from this line to that line, and this line here is y over 3. This line it will be y. Y over 3 should actually be thought as x equals to y over 3. Okay? Alright, so maybe I should just erase this because it might confuse later. Alright, so coming back from 5 to 15, what happens? Well, you start from the same line. It's still y over 3 that you start. But you end right here in a vertical line. This equation is x equals to 5, right? So you should really put 5 here. Okay, so that's how you would represent this integral using two integrals rather than one. But not only is the second one harder, when you try to integrate by x, you will find that this integral is impossible to do. No matter what you use, whether you use integration by parts or whether you use U-Substitution, none of the methods will work. And if you're curious, then you can even put this into Wolfram Alpha or some other integration packages, and they're going to spit out answers that you don't understand because it has to define something called error function. It's just really crazy. Okay, so since we have to integrate one or the other, but this is impossible, so we're back here. We have to integrate this one. Let's do that. Remember, this is a partial integration, so you're treating x as a constant. So although this looks horrible, if you know how to integrate 4 dy, which is like 4y plus c, right? The same thing here. If you integrate this, this is a number, so if you integrate, it just gives you y. And then you have to plug in 3x and x. And then you integrate 0 to 5 dx. Let's see, if you plug in 3x, and then you subtract x, then you get 3x minus x, which is 2x. So overall, you get 2x cubed e to the x squared integration from 0 to 5 of dx. Okay, now here comes a slightly challenging part, which is U-Substitution. This unfortunately requires both U-Substitution and integration by parts. So let me show you U-Substitution first. U set it equal to x squared because that looks like a nested function. Du is equal to the derivative of x squared, which is 2x, and then you attach a dx. And therefore dx is, if you solve this for the dx, is 1 over 2x times du. So we are ready to do a change of variables and another thing is, since u is x squared, when x is 0, u is 0, but when x is 5, u is 25. That's one piece of information that a lot of people have missed in Calc 2, so hopefully you know that you have to do that in this case. Okay, so you have 2x cubed e to the u, and dx is 1 over 2x du. So 2x and one of the 2's and one of this will get be cancelled, and you end up with 0 to 25 of x squared of e to the u du. And it's very important to actually make sure that you don't have any more x's left, because when you do U-substitution, you should completely change everything to u. If you still have an x in there, then you have not finished doing the U-substitution. But this is relatively an easy situation because x squared is equal to u, so I can just replace x squared by u, and we get 0 to 25 of u times e to the u du. And that is still another integral requiring a special method. In our case, we will call this, we will use the tabular integration. Tabular integration is a method that's equivalent to integrate by parts, but this happens to be a lot easier than integration by parts, at least in my opinion. So if you don't know how to do tabular integration, please search up tabular integration on my channel. There are several videos that I have titled as Introduction to Tabular Integration, and those should be really easy to follow. Okay, so what do? Tabular integration says one part has to be differentiated, whereas the other has to be integrated. And then the differentiating one, you keep differentiating until you hit 0. And then the part where you integrate, you keep integrate until you're at the same level where you stop differentiating. And e to the u is really easy to integrate, right? And then this column, the first column is the alternating signs. You always start from plus and you go down plus, minus, plus. Okay, once you're done with this, then the tabular integration says first you do that. It's like a missile going down, like, yeah, that's how I see it. So you end up with u times e to the u, -1 times e to the u, and the last one has to be multiplied and integrated, but 0 integrates to just a constant, and because we're doing definite integrals, constant doesn't come into play, so we don't really need that. Okay, so that's all we have to do. That's actually, hopefully you can see why I choose to do tabular integration over the traditional integration by parts. Anyways, you have u e to the u minus e to the u, and you have to plug in 25 and 0, which gives you 25 times e to the 25 minus e to the 25 minus, when you plug in 0 into u, this is 0, but negative e to the 0 is what you have. So that's -1, and you have to subtract it. So you're subtracting -1, which means you're adding 1. And you can even these are like terms, so you can combine them. 25 minus 1 is 24, so you have 24 e to the 25th power plus 1, and that's the answer.